For this one, I can use synthetic division because I've got a binomial of the first degree with the leading coefficient of 1. So I take the opposite of this thing, which is going to be a -3, and I put it in my box. Now I write down my coefficients in descending order. I've got 2, 0 because I'm missing the x squared, the 4 and the -6. So now I bring down the 2. I multiply what's in the box times what's underneath is a -6. I add straight down. I multiply. That's an 18. I add straight down. I multiply, and I add straight down. And now I bust out my secret decoder ring here. Since this thing started with an x cubed, my answer is going to start with an x squared. So this translates into a 2x squared minus 6x plus 22 with a remainder of -72, which goes over the thing I was dividing by. And that's it. That's synthetic division. With something like this next piece, I can't use synthetic division the way this thing is written, but if I divide everything by 3 first and essentially turn the problem into this, this would be a 2t cubed plus 5 thirds t squared minus 2/3 t plus 1/3. That would essentially be my numerator. It's like multiplying numerator and denominator by a 1/3. My denominator would then be a t plus 1/3. That's essentially the same problem. In this one, I can use synthetic division. So I put the -1/3 in my box. And I write down my coefficients, the 2, the 5 thirds, the -2 thirds, and the positive 1 thirds. I bring down the 2, I multiply, that's a -2 thirds. I add straight down, that's a 3 thirds, which is 1. I multiply, that's a -1 third. I add straight down, that's a -3 thirds, which is a -1. I multiply, that's a positive 1/3. I add straight down, which is a 2 thirds. And so now what this translates into is a 2t squared plus t minus 1 with a remainder of 2 thirds over the thing I was dividing by, which is a t plus 1/3. And I can't leave it like that. That's not acceptable to have this as your answer, because that fraction at the end, that remainder, I can't have a fraction with any fraction. Okay, so I get this enormous stacked fraction. So what I do is I multiply this by 3 over 3. In the numerator, see what happens here. In the numerator, that just gives me a 2. In the denominator, I distribute the 3, it gives me a 3t plus 1. And now I'm back to the original thing that I was dividing by in terms of my remainder. Okay? For this, the first thing I want to do is identify increasing and decreasing. So for this one, it's decreasing when it looks like a negative slope, increasing is positive slope, and essentially it's when we're going left to right in terms of the x, is it going up or down? Okay? So for this one, looks like the function is decreasing until I get to here, and then it increases, and then it decreases again, and then it increases at the end. And so what I want to do is I want to label the intervals. And remember, at these turning points, it's not increasing or decreasing. So now I'm just going to label the intervals. It's increasing from here to here, so that's from a -3 to a 0. And then it's also increasing from this value on up, so it's increasing from 3 to infinity. So that's my increasing sections. For decreasing, it's decreasing from this end until I get to here, so it's decreasing from -infinity on my x until I get to -3. And then it's also decreasing from here until this value. So it's decreasing from 0 to +3. And that's it, increasing, decreasing. I write it in interval notation. In terms of relative maximums and minimums, relative max is a relative high point, which is right here at 0, 0. And again, it's when the function goes from increasing to decreasing. Relative minimums, there's 2 of them. They're just relative low points. And again, this is where the function goes from decreasing to increasing. So I've got one at -3, -4. I also have one at 3, -6. So I get 2 of them. And then the end behavior, I'm just looking at the end. So I just look as x goes to -infinity. I look as x goes to +infinity. As x goes to -infinity, that's the left side of my graph. The function is going up. So f of x goes to +infinity. As x goes to +infinity, I'm looking at the right side of my function, the right side of my graph, which is also going up. So f of x goes to +infinity again. And that's it. Okay, that's the notation for end behavior. In number 21, I essentially do the same thing. So left to right, it's going up, so it's increasing. And then it's going down, so it's decreasing. and then it heads back up again, so it's increasing at the end. And then once again, at these turning points, it's not increasing or decreasing. So as I look at increase it was increasing from here until I got to here, so it was increasing from negative infinity until negative 2. And then it's also increasing from here on up, so it's increasing from a positive 1 until infinity. And then for decreasing, it's decreasing in between these two values from here to here, so it's decreasing from negative 2 to positive 1. And again, we use parentheses because none of those values are included. That's interval notation. And then relative maximum, there's one right here at negative 2, 3. And then a relative minimum, there's one right here at 1, negative 3. And then the end behavior is x goes to negative infinity, and then as x goes to positive infinity. As x goes to negative infinity, I'm looking at the left side of my graph. F of x goes to negative infinity. As x goes to positive infinity, that's the right side of my graph. F of x goes to positive infinity. Okay, that's my end behavior. If I look at end behavior algebraically, when we're in standard form, we essentially just look at the thing that has the highest exponent. So this one, I'm just looking at that term. So I'm just going to plug in the negative infinity, and then I'm going to plug in a positive infinity and see what my f of x values do when I plug those values in. And really, this becomes a game of signs as I plug this thing in here. So if I plug a negative infinity in, negative infinity to the 6th power is a positive infinity, and then times the negative 2 is a negative infinity. And then if I plug a positive infinity in, I get negative 2 times positive infinity to the 6th power is also positive infinity. So I get a negative infinity once again. Okay? That's my end behavior. When I don't have this in standard form, I just plug the positive or negative infinity in for each. So I still do as x goes to negative infinity, and then as x goes to positive infinity. When I plug the negative infinity in, right here I have a negative infinity squared, which is infinity. And then I tack on that negative sign, times a negative, times a negative. And when I multiply all these together, that's going to give me a negative. If I plug a positive infinity in, again, positive squared is going to be positive, and then I tack on this negative sign out front, times a positive, times another positive. So that also gives me a negative once again. Okay, and that's it. For this one, we want to sketch a possible graph, and we'll get the calculator out to identify relative maximums and minimums. But to start with the x-intercepts, I'm going to find that x equals 0, x equals 4, and x equals a negative 3. And I already know a couple things about this graph here in terms of the x-intercepts, and then really I can get the general shape of this thing just by identifying end behavior and multiplicity. See, each of these values occurs one time, which means I'm going to pass through the x-axis each time. And if I identify end behavior, what x is doing on each end, if I plug the negative infinity in, that's going to give me a, let's see, negative times a negative is a positive, times a negative times a negative, that's a positive infinity. And if I plug a positive infinity in there, it's going to give me a negative infinity out, which means on this end of my graph, I'm going to be going up. At this end, I'm going to be going down, which means our graph has to look something like this. And if I want to graph this with a little bit more accuracy, I'm going to go find these local maxes and mins using my calculator. So I'm going to go to the y equals menu. So I hit y equals. I'm going to punch this thing in. So my graph looks a little bit something like this. I'm going to go to the window to make it a little bit taller. So I'm going to change maybe the y maximum to something like 15 or 20. I'll go 15, just so I can see the top of this graph a little bit better. And now if I want to calculate the local max and min, I go to second, calculate. I'm going to do the minimum first. Left bound, I go to the left of that point, and I hit enter. And then I go to the right of that point and hit enter, and then take a guess and hit enter. And so what it does is it tells me that this minimum value right here is at a negative 1.69 comma negative 6.3. So that's going to round up to when it's all said and done. And then I can do the same thing with the local maximum. So I go to second, calculate, down to maximum. Can I go to the left of that value? Then I go to the right, and I hit a guess. And it gives me about a 2.36, comma 10.37. Okay, so it gives me a little bit more depth and a little bit more accuracy in terms of my graph. Okay. Next one is the same thing. I find each of the x-intercepts, so x equals 0, x equals a -5, and x equals 2. In terms of multiplicity, this one occurs twice, this one is once, and this one is also twice. And then with just the end behavior, if I plug a negative infinity in here, I get a negative infinity out. If I plug a positive infinity in here, I get a positive infinity out. And so now if I plot each of these, I've got the 0, the -5, and the positive 2. I know that at 0 and at x equals 2, I'm only going to touch the x-axis, while at -5, I'm going to pass through. I know that this end has to open down. I know that this one has to open up. So essentially, I know that the graph is going to look something like this. It's going to pass through, touch, touch, and then continue up forever. All right. And then if I want to get a little more accuracy with this thing, once again, I go to my calculator. And so what happens here is I have to adjust the window once again. So now I can see that first maximum, so I go to calculate. I do left bound, right bound, take a guess. So it looks like that maximum is right here at -3.84, comma 583.4, something like that. 0.37, I guess, since I rounded the other one 2 places. This local minimum I already have, that's 0, 0. This local minimum I also already have, it's 2, 0. So the only other thing I need to find is this local maximum, which I'm going to have to zoom in a little bit further. So I'm going to go back to zoom standard here. And now I can see that with some accuracy. So I calculate. It looks like this value right here is at 1.04, comma 6.02. This one just stating whether or not this is a 0 of the function. I can check it with synthetic division. I put the 2 in the box. I write down my coefficients, the 3, the -7, the -4, and the 12. I bring down the 3, I multiply, I add straight down, I multiply, I add straight down, I multiply, I add straight down. And I get a 0 here, which means, yes, this one is a 0 of the function. That's how I test it. Doing the same thing with a -3 and a new function. I've got a 1, a 0 for the missing term. And I bring down the 1, I multiply, I add straight down, I multiply, I add straight down, I multiply, I add straight down, I multiply, and I add straight down. And so for this one, I get a 24, which means no, this one's not a 0 of the function. When I plug it in, I get a 24. If I look at this one, this time I'm giving you a 0, so I'm telling you that 4 is a 0 of the function. So if I divide out that 4, using synthetic division, I can finish factoring this thing. So I bring down the 1, I multiply, I add straight down, I multiply, I add straight down, I multiply, and I add straight down. So that means if x equals 4 is a solution, x minus 4 is one of my factors. My other factor is right here. It's x squared plus 8x plus 15. And now I can finish solving this thing. This factors into an x plus 5 and an x plus 3. And now I set each factor equal to 0, so I get a 4, a -5, and a -3.